All right, so we're gonna go back to our carbohydrate topic, and we're gonna explore now open chain and ring forms of monosaccharides. So let's dive in. Because aldehydes and ketones, that carbonyl has a partial positive charge on the carbon, and because an alcohol oxygen is nucleophilic, when aldehydes get attacked by alcohols, I'm gonna form a hemiacetal. And when ketones get attacked by alcohols, I'm going to form a hemiketal. So if you take a look here, what ends up happening is my hydroxyl group here is what attacks my electropositive carbon. And then, of course, the electrons within this bond have to kick up, which is why I see this OH. Typically, I'll pull that hydrogen from somewhere else. I actually see a very similar mechanism exist for a ketone and an alcohol. Again, in this case, the hemiacetal, right, has this functional group where it's an OR, right, that's differentiated, whereas a ketal, right, will actually have two R groups as opposed to an R and an H group. This is how I form the ring forms of my sugars. So pentoses and hexoses readily undergo intermolecular cyclization. So the carbonyl carbon becomes a new chiral center, and this is what we refer to as the anomeric carbon. So, for example, D-glucose exists in one of two forms, the alpha, which is down, or the beta, which is up. So the carbonyl oxygen becomes a hydroxyl group, and it's the position of that group that determines whether something is alpha or beta. If the hydroxyl group is on the opposite side, trans, of the ring, then it's going to be alpha. If the hydroxyl group is on the same side of the ring as the CH2OH, then that configuration is going to be beta. So this low energy form in a ring is actually very important for the reactivity of the ring itself. So because of this ability to form a hemiacetal, it actually is a six-membered ring that's formed if it's a hexose that resembles pyran or pyranosides, and then a five-membered ring that resembles furan or furanosides. So let's take a look. This shows the Fischer projection for D-glucose, and then you can actually see the attack of the hydroxyl group onto the carbonyl carbon, and that is going to form either alpha, where the hydroxyl group is down, right, trans from the CH2OH moiety, or cis, where the hydroxyl group is on the same side as the CH2OH moiety. So pyranoses are the six-membered oxygen-containing rings, and furanoses are the five-membered oxygen-containing rings. And again, we typically draw the anomeric carbon on the right-hand side. So if you take a look at the structures that are shown here, so alpha-D glucopyranose or alpha-D fructofuranose, you can actually see the way in which I've numbered the carbons. That's going to be key for you, particularly when you are identifying both enantiomers and the anomeric carbon. And I've also shown pyran and furan, which are the namesakes for these sugars. Because the ring form exists in equilibrium with the open chain form, we can actually test for the presence of what we refer to as reducing sugars. So if I think about these anomeric carbons and their special reactivity, right? The ability to look at, say, for example, the chair boat versus the boat conformation for the chair structures, there's going to be some steric crowding, right? And I want my bigger groups to be equatorial. And really what I care about is the fact that if I can oxidize an aldehyde to a carboxylic acid, right, then I consider my aldose to be a reducing agent. So a test for reducing sugars is, for example, Fehling's test. This is where I convert copper 2+ to copper 1+. And that's the deposition of Cu2O, which is red. Likewise, my aldehyde can also reduce silver to silver 0. That's the Tollens test. That's formed via the deposition of metallic silver or a silver mirror. And that allows us to determine whether or not I have a reducing sugar. Remember, oxidation is the loss of electrons, reduction is the gain of electrons. If I have a reducing agent, that's something that's being oxidized. So in this case, the aldehyde is being oxidized up to the carboxylic acid. It's really important for us to think about important hexose derivatives because this is going to give us a key into both the types of molecules that we see and the types of reactivity that are important. And so you can see here the glucose family and some of the derivatives therein. You can actually also see some of the amino sugars, as well as some of the deoxy sugars, and then some of the sugars that actually get converted to acids, and then the lactones that we'll talk about shortly. So I can join two sugar molecules via what's called a glycosidic bond. So that's the bond between an anomeric carbon and a hydroxyl carbon on a second ring. So the glycosidic bond, or the acetal, between monomers is less reactive than the hemiacetal at the second monomer. So if I have a second monomer with a hemiacetal that's reducing, the anomeric carbon then that's going to be involved in that linkage is non-reducing. So a disaccharide that's formed upon condensation of two glucose molecules via a 1,4 bond, I'm going to refer to as maltose. If you take a look at the formation of this bond, you can see a couple of things. One, right, I have my hemiacetal, right, where this is my R, this is my H, this is my OH, and this is my OR. And I have my alcohol on another sugar. And so if I do condensation where I have the loss of water, I form a bond between those two groups. That's referred to as an alpha 1,4 bond, alpha because of the anomeric position, between glucopyranosyl and glucopyranose. I could also join two sugar molecules via a glycosidic bond between two anomeric carbons. So that's two acetal groups and no hemiacetals. That means there's no reducing end, so that's a non-reducing sugar. So trehalose is a constituent of the hemolymph of insects, and it provides protection from drying. You can think about it in terms of the resurrection plant, for example. These are examples of sugars that have very specific reactivity simply because they're no longer reducing sugars. Here are a couple of other great examples. So here's lactose. And there's also sucrose, and then the trehalose that we spoke about before. Here you can see the beta 1,4 linkage, the alpha beta 1,2 linkage, and then an alpha 1,1 linkage. Now we're going to talk in a little bit more detail about polysaccharides themselves. So these are natural carbohydrates. We typically find them as polymers. They can be homopolysaccharides or heteropolysaccharides. And it's not uncommon for us to see them as either linear or branched. They typically do not have a defined molecular weight. That's in contrast to what we think of in terms of proteins, because there's really no template that's used to make these polysaccharides. You can see here homopolysaccharides that are unbranched versus branched. You can actually also see for the heteropolysaccharides, these are more than one type of monomer, and they also can be either unbranched or branched. So we're going to pick up looking at some biological functions of polysaccharides in the next section. Thanks again.